Hello students and welcome to this calculus video. Going off of our last video, we were looking at how to use optimization in particular problems. In this video, we're going to go through 3 more examples. So let's get started. All right, so in example 2, we have a box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long. We're going to be cutting out the square from each of the corners and then bending up the sides. If you haven't done this before, it's actually really good practice to actually making a box if necessary. So find the size of the corner square, which will produce a container that will hold the most amount of soup. A little bit weird that we're holding soup in cardboard, but we don't know what type of cardboard it is, what's been treated to it, but let's go ahead and look at this problem. Let's answer this question. I know it's a rectangular piece of cardboard, so let me draw a picture real quick. So here's a rectangle, and I have X and Y, but we also know that this is 25 centimeters wide. So I'm gonna go 25 there, and 40 centimeters long. So I'm gonna go 40 right there. And we're cutting out a square from each corner. So I'm cutting out a square, so from each corner. And that is what is going to get me some sort of value. So let me erase the X and Y variables that I put, because we know that the length of the cardboard is 25, and so we know we're going 25 by 40. But we're cutting out these squares, and the size of the squares are always going to be the same. So find the size of the corner square, which will produce a container that will hold the most amount of soup. Okay, so we want to also find some sort of box shape. All right, so let me draw a box real quick. Again, I'm no artist. Okay, and that's pretty much what I have here. So as you imagine this, what you kind of want to notice is that, okay, I'm cutting out these squares in the box, and as I fold it up, the height of the box is going to be that square. So then that's going to be X. Well, what is the length and the width going to be? As I do this here, that length and the width, well, we're cutting out X. So I'm subtracting X from right here, and I'm subtracting X from right there. So that's going to be 40 minus 2X right there. Okay, and then the other side length is going to be 25 minus 2X. So 25 minus 2X. So what do I want to maximize? Well, I want to maximize volume, right? How do we know how much soup is going to be in there? Well, we measure that using volume. So let me write out my equation for volume. Well, volume is going to be length times width times height. So that's going to be X times 40 minus 2X times 25 minus 2X. And we want to maximize this. In order to maximize this, I need to take the derivative. I think it'll be a lot simpler if I actually distribute everything. So let's go ahead and spend the time to actually distribute here. Okay, so that's what I got when I distributed and multiplied everything out, and I just kind of wrote in combined like terms in standard form. All right, what do I want to do? So in order to maximize things, you need to be thinking, okay, how do I find the maximum? Well, that's going to be with the first derivative. So let's find b prime here. And so that 4 times 3, that's going to get me 12x squared minus 260x plus 1000. And what do I need to do with this? Well, I need to set this equal to 0. So I am going to kind of move it over here to the side, but let's see what I can factor out from here so that maybe I can make this a little bit easier. So 12, 260, 1000. All right, I can divide each of those by 4, and then 0 divided by 4 will still get me 0. So I can write this now by 3x squared minus 260 divided by 4 gets me 65x, and 1000 divided by 4 gets me 250. So plus 250 equals 0. So now it makes it a little bit easier for me to factor. The factors for this are going to be 3x minus 50, and they're going to be x minus 5. Okay, and then we're going to set that equal to 0. So what are the values for x that I get? Well, I'm going to get x equal to 50 over 3, and I'm going to get x equal to 5. So now I have to make a sign chart. So let's do that right here. Again, we're going from 0 to infinity. So then We have the sign chart. 50 divided by 3 is going to be greater than 5. So I'm going to put 5 here and 50 divided by 3 there. And I'm going to substitute it into my factor form, 3x minus 50 and x minus 5. So let's substitute 1 in there. So I get 3 minus 50. It's going to be negative. 1 minus 5. That's going to be negative. So this is positive. A value between 5 and 50/3. So this is where I actually need. I'm going to go with 6. So 18 minus 50, that's negative. And 6 minus 5, that's positive. So this all comes out to be negative. And let's go with 100 in the next one. So 300 minus 50, that's going to be positive. And 300 minus 5, that's positive. So this is going to be positive. Well, we want to maximize. So where do I maximize in this sign chart? Well, I get a maximum. So let's actually write here, volume is maximized when x equals, so is it going to be 5 or 50/3? At 50/3, we're going from negative to positive, and at 5, we're going from positive to negative. So that gets us the maximum at 5. So when x equals 5. So this is where you actually need to determine which of these you're actually going to use, because 50/3 would be a minimum. We don't want the minimum amount of soup. We want the maximum amount of soup. So what is the size of the corner square that we're going to cut out? So we know volume gets maximized when x equals 5 because v prime changes from positive to negative. Okay, so now we need to say, all right, what is the size of the corner square? So the corner square that we're going to cut out is going to be, so this is measured in centimeters, so 5 centimeters by 5 centimeters. That's what we need to cut out of that cardboard to get the maximum amount of soup. So we're a soup manufacturer and we are trying to maximize the amount of soup that we can put in a box and limit the amount of waste that we're producing. We're going to cut out this size of a square from the box so that we can maximize our profits and maximize the happiness of our customers. All right, let's go ahead and begin looking at our next problem. We have a rectangular page is going to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5, and the left and right are going to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? So least amount of paper, and we're talking about area because we want to make sure that we're not wasting paper. We need to save those resources. So we know we're gonna want a minimum. Let me just kind of draw a picture here. And of course, I've already made these notes and I've already gone through these problems and I have experience solving these problems. But I draw these pictures for you guys because it's that important. If you don't know how to tackle a problem initially, you're going to want to kind of think critically and you're going to want to go through these problem solving steps. So that's kind of why I do it with you. All right, we know it's going to contain 24 square inches of print. The margins at the top and bottom are to be 1.5 inches. So 1 1/2, and this is 1 1/2. And then the left and right are going to be 1 inch there and 1 inch there. So we've got all this writing and it can only happen within the confines of this page. So, all right, what are the length and width of the page? If I label let me kind of draw a box of where we can right now. So this is going to be X and we're going to call this Y. So what is, we want to solve for the outer part of the page. So the outer part of the page, if I were to do all of the X or all of this part here, well, I can measure that saying that that is X plus 1 plus 1. So that's X plus 2 going across the top and across the bottom. And on the sides, if I were to measure all the way from the top to the bottom, well, that's Y plus 1.5 plus 1.5. So Y plus 3. We know that we have the 24 square inches. What do I want to maximize? Well, I want to maximize, or I want to minimize the outer part. I want to make sure I don't have any wasted paper anywhere because my goal target is 24 square inches of print. I'm going to say the area equals X plus 2 and Y plus 3. And you notice a problem is that we have two variables. So I need to solve for another variable here. So that's where this 24 square inches of print, that smaller part is going to be 24 equals X times Y. So I can solve for one of those variables. Let me solve for y here. So I'm gonna get 24 divided by x equals y. So now I'm gonna make that substitution up into that equation above. So a equals x plus 2 and 24 over x plus 3. So now what do I want to do with that? Well, I want to find the derivative because my goal is to minimize this. So a prime, okay, and actually I think it'll be easier to distribute everything first and then find a prime. So if I distribute the x, we're gonna get 24 and then plus 3x plus 48 over x and plus 6. Okay, so let's, do I have any simplifying I can do here? Yes, I have a little bit. So 30 plus 3x plus 48x to -1. All right, so using that, let's actually find my derivative. All right, so I'm gonna get 3 and then minus 48 over x squared. Let me just kind of write it like that. And we want to set this equal to 0. So I'm going to get 3 equals 48 over x squared. Solving for x, I'm going to get x squared. So 3x squared equals 48. And divide that by 3 is going to get me 16. And then the square root of 16x will get me 4. Okay, let's see what we found now. Okay, we're going to go to a sign chart. I'm going to put 4 in there, so 0, here's 4, and this is going to represent a prime. So if I have a value, let's use 1, because that's in between 0 and 4. I'm going to get 3 minus, so I just want to point out that I am using the equation that's right there. So 3 minus 48 over 1, so that is going to be a very negative value. And then if I do a value that's greater than 4, let's do 100. So 100 squared, very large number. 48 divided by that is going to be very small. So 3 minus that is going to be, you know, it's still going to be positive. Okay. So we know that we have, because it's going from negative to positive, we have a minimum amount. We're going to state that we have a minimum because a prime changes from negative to positive. So now what are the dimensions of the page? So the dimensions, well, those are going to be, all right, so I have x plus 2 there. So that's 4 plus 2. So that's going to be 6 inches. And then we need to figure out what y is. So I'm going to use this equation that's right here. So using this equation here, okay, I know, all right, 24 divided by x. So x is 4. So 24 divided by 4 is 6. So then I'm going to get 6 equals y. And I'm going to use now this because y plus 3, that's going to get me the dimensions of that vertical side of the page. 6 plus 3 is 9. So that's 6 inches by 9 inches. Those are the dimensions of the page. That gives me 24 square inches of print and the margins that I'm looking for. So there's a lot of reasoning behind what the standards that we use on pieces of paper, on certain boxes and shapes. So we keep that in mind as we're doing as we're going through life, because, you know, they minimize waste, they maximize profits, and you know, that's just because of calculus. People have done those calculations. So now let's go ahead and look at example 4 now. So now looking at our final question here, we have a rectangle bound by the x and y axes and the graph of y equals 3 minus 1/2 x. What length and width should the rectangle have so that its area is a maximum? So we want to maximize this rectangle, sorry. So I'm going to say that horizontal distance is going to be x and that vertical distance is going to be y. So in order to figure out the x and y, so we want to maximize the value. So I'm going to say a equals x times y. Well, we already have an equation that we can use to substitute here. So I'm going to say that a equals x and then y is going to be 3 minus 1/2 x. So let's simplify this. So 3x minus x squared over 2. And let's take that derivative. Just the exact same thing that we've been doing in all of our other equations. So a prime is going to be 3 minus, bring the 2 down. So that's going to just be minus x. So let's set this equal to 0. And when I do that, I'm gonna get 3 equals x. So what is the length? Well, we now know that the length is 3. So how do we find the width, the height of this rectangle that's being bound by the x and y axis and that line that we're given? So now I'm going to just substitute the 3 in for x. So I'm going to get y equals 3 minus 1/2 times 3. So 3 minus 1.5. So y is going to get me 1.5. The other thing I have to do here is, I've kind of done this a little bit out of order, but it doesn't really matter, is I still need to show that this 3 that I found is going to be, actually, I don't want to say that this is being a 0 because we do have the x-axis going from -infinity to +infinity. But I guess it is bound by the y-axis. So yeah, we can cut this off. All right, so 3 goes there, that's a 3. And this is going to be representing a prime. So let's see, substitute a value in between 0 and 3, that I'll substitute 1 in. So 3 minus 1, that gets me 2, so that's positive. And a value greater than 3, so 4, 3 minus 4 is negative. So we know that we are getting a positive to negative, so that proves that we have a maximum. So area is maximized because a prime changes from positive to negatives. So then the length and width should be, we're going to say the dimensions are 3 by 1.5. If this were inches or something, we would have that. So length is going to be 3, the width is going to be 1.5. And that is going to conclude this video, because I know that slogging through this lesson is going to be really tedious because there's a lot of algebraic stuff. There's a lot of substitution, but there is kind of a pattern that you want to see emerging here. So we've got 2 more videos filled with 4 more examples before you actually get to your homework. So stay tuned. Of course, if you do need help on any of these problems that were in this video, please reach out to me. I'm Mr. Hernandez, and this was Mr. Hernandez Teaches.